So the next speaker today is Danila Cherkashin. He is from St. Petersburg, Moscow. Moscow means MIT. He will speak about panchromatic colorings.
Thank you very much. There is a problem with camera that it... Короче, камера настроена, да?
Тут я не умею ничего сделать.
Okay, so let me start. Thank you very much for the invitation. I'm glad to speak here. Not to be boring, I decided to speak without presentation, but with a back button. So let me start. I will speak about panchromatic colorings of hypergraphs. What does it mean? Panchromatic coloring is a vertex coloring. Such that every edge contains a vertex of every color. Every edge, this is a set of edges, contains the problem about such colorings, as far as I know, was not very precisely stated by Erdős and Lobos, because in their very seminal paper with local Lobos lemma, they applied this lemma to show the result that if every edge intersects at most this quantity of edges, then an uniform hypergraph has a panchromatic colorings with air colors. So if every edge intersects not very much hyper edges, the panchromatic coloring exists. So n uniform graph admits air coloring. Then Alexander Kostechka stated the problem in the form in which I will speak about. Kostechka asked about the quantity P on an R, which is the minimal number of edges in a hypergraph without panchromatic air coloring. In a uniform hypergraph, without panchromatic air coloring. Then he linked it with choosability problem on graphs, and in a joint work with Woodall, they linked this with Hall ratio. So they proved some criteria on the existence of panchromatic colorings in terms of Hall ratio. Also, Kostechka gives very simple bounds, which use Erdős, Rubin, and Taylor theorem, that there are some constants, C1 and C2, positive constants, that this bounds holds. So even here one may see that the quantity PNR has growth like exponential in some power n divided by r. In fact, we will see it now that one can put C1, C2 equal to 1 with another functions here. So let us speak about upper bounds first. So upper bounds. There are several upper bounds for different ranges of n and r, and in my talk I will speak about the situation when r is big when competing with n. Okay? So the is big and is small. So obviously this inequality should hold, because otherwise the problem has no sense. Okay, the best upper bound now in this situation is the bound of Shabanov. Unfortunately, he is not here, but he will speak tomorrow. Yes. Mm-hmm. Okay. So the bound of Shabanov was the following. So one may see that this quantity is very similar with this quantity, exponential in the power of ratio n and r. Yes. So just this form is more convenient if we speak about probabilities. Okay, then the first of my result is that if r is greater than n power 2 divided by 3, we have that not greater than n ln r. So, in fact, I can prove this theorem for any range of n and r, but for this range it is better than the previous one. Okay? So, the methods to prove both this theorem by Shabanov and mine theorem is to consider the quantity, I call it prime, and which is in fact it is minimum from two random numbers v m. If someone knows what it is. If you don't know, I can define it directly. It is the minimal number of edges of n edges which one needs to just to how to say that every set of size, every set which tree of size at least contains an edge. Okay? So it is a minimal collection of n edges on v vertices such that every H every big subset of vertices contains an H. Obviously, we have the inequality P and R like then P prime and R. Because by pigeonhole principle, one has that there is a color. If we consider any coloring, there is a color of size less than the number of vertices divided by R. So the remaining vertices has size at least this number, and there will be an H in the remaining vertices. Okay? So this inequality is obvious because the minimizer of this property doesn't admit a panchromatic coloring. Okay. Then both me and Shabanov used standard F' method to construct random hypergraph such that to prove that there exists a hypergraph doesn't admits this property, so it doesn't admit the panchromatic coloring. But Shabanov was interested in the small values of R with comparison with N, and so he doesn't very precise in calculations. So let us go to lower bounds, and this is the main part of my talk, because the proof of upper bound is rather technical, and the proof of lower bounds is rather theological. Okay, so again, there were different bounds for different ranges of R and N and R, but I still interested in the situation when R is big and N is small. Okay? So with comparison to each other. Okay? So then the best bound, the best. Okay, 1 minute. Sorry, I forgot it. So I forgot to write it down. Nevertheless, there were a lot of interesting bounds by Shabanov and Rozovskaya. So I forgot it. I forgot to write it down in my paper. So I cannot write it down now. But there was some nice bound. There were some nice bounds. Nevertheless, there were a problem when such that if R is greater than N divided by logarithm of N, then with some constant, maybe 10 is enough. Then there is no bound. There was no bound on P and R. The reason of it is the following. Suppose that we gonna use some probabilistic argument to prove a lower bound. So we want to consider random coloring in some sense, and then evaluate some probability. And when then we always gonna use union bound on the probabilities. But the probability that in uniform independent color vertices an H has doesn't contain a color is like this. So it is greater than 1, but it is the bound from union bound. Okay? So we have such probability that it has no color 1, the same probability that it has no color 2, and if we want to use union bound, we should multiply it by r. And then we got that we evaluate the probability in a very bad way, that this probability is greater than 1. Okay? So the standard probability argument doesn't work in this case. One of the main theorems is that P and R is greater than this value. What does it mean? Note that it depends, first, note that it depends only on such ratio. It doesn't depend, and it doesn't have any, so yes, if you have an abstract of talks, then there are some bounds written here, some lower bounds. And all the lower bounds has some, have some algebraic function, depends on n and r, which is greater than such exponent if the ratio of n and r is small. Okay? So this bound depends only on the ratio of n and r shifted on 1. It doesn't matter if n and r is big. Okay? So how to get this bound? Let us color not in R. Let us try to color our hypergraph not in R colors, but in some number A greater than R colors. Okay? Then we can note that in fact this quantity is not bound on probability, but in fact a bound on expectation. So it is the expectation of such colors that this is the expectation of number of colors that an edge doesn't contain a fixed edge. Okay? So if we multiply it on number of edges, we have the not the bound, but the expectation of the number of bad pairs that it is an edge and it is a color. Yes? So expectation of expectation of number of bad pairs. Okay? If we consider the uniform random color dependent on every vertex, the expectation of such pairs that H, E doesn't contain color I is as follows. Then, if it is less than A minus R, we may say that with positive probability there is such a coloring that only this quantity of colors does not meet every edge. Okay? And then we can say that let us. It means that there is are proper colors, and they realizes the panchromatic coloring. They realize panchromatic coloring. So with positive probability, panchromatic coloring exists. Note that this theorem doesn't admit a local version because it used the excitation argument, and so there is no chance to apply local lowest lemma or something like this. So there is another approach to get a better result in the case when such that we will use only local arguments. This is the approach of some geometric approach, which is in fact rethinking of Anders Plukhaar ideas. Let me tell about it more precisely. So there is an Anders Plukhaar theorem about greedy colorings. Let me tell it. First, let me recall the definition of standard proper coloring. Proper coloring of hypergraph in R colors is a vertex coloring such that there is no monochromatic edge. No monochromatic edge. Okay? Then Anders Plukhaar theorem says that the existence of proper coloring is equal to the existence of a proper order of vertices. It means that order is proper if there is no such a collection of R edges in this order that the vertices of that the first edge intersect the second edge in exactly one vertex. So E equal A plus 1 is 1, and all the vertices of the first edge lies in this order earlier than the vertices of the second edge lies earlier than all the vertices of the third edge in last. So, and the total number of edges is R. So in the first edge is the rth edge. Okay? What does it mean? In fact, it means that we can color our hypergraph greedily. Let me prove this theorem first. Let me prove this theorem. So the it is very simple in both sides. First, if we have a proper coloring, then one can consider the following order. This is the vertices of the first coloring, of the first color in arbitrary order. Then the vertices of the second color in arbitrary order. And as follows, here the vertices of R of R scalar here in M in R colors is M proper. And let us see that there is no such chains in this coloring, because if we have such a chain, then this vertex has at least color 2, this vertex has at least color 3, and this vertex has at least color R, and so this edge is monochromatic. Okay? So in the second, from the right to the left, the proof is very simple. Let us try to color our hypergraph grid. It means that we consider our order, goes from left to the right, and try to color current vertex in the minimal color, such that there is no monochromatic edges in this part. So suppose the contrary, that we cannot color in this way. Then it turns out that there is a monochromatic edge with color R. Because otherwise we can color, if the color is not R, we can color in higher color to and this edge not be became non-monochromatic. So this vertex, the first vertex of this edge, should be colored in color R. It means that there exists an edge such that it's its last vertex, and all other vertices colored in colors R minus 1. R minus 1. Okay? Otherwise, by our algorithm, we can color it in color R minus 1, the last vertex. So this vertex should be colored in color R minus 1 too. So there is an edge which is almost monochromatic and has all other vertices of color R minus 2. So going as follows, one can finally came to R chain, ordered R chain. So contradiction. We proved this theorem, and it's a very beautiful theorem, and it gives a lot of new methods and bounds in hypergraph colorings. Then let me say why it is useful in our case. Consider the very simple case, R equal to 2. Yes? Then one can say that one can note that we can get a coloring from the order in another way. And its way is the following. If you have an order, and if you can have an edge, then let us try to color the first edge, the first vertex of this edge in the color 1, and the last vertex in color 2. Then if we have a contradiction, so this method doesn't work, it means that we have exactly a vertex which should be colored in the first and the second color at the same time. So it means exactly that there is a chain. Okay, so let us try to apply this in our case. Let us consider a simplex with R vertices, exactly R vertices in R minus 1 dimensional. And let us consider its edges. Then we are going to try to map our vertices randomly at the simplex, at the edges of the simplex. After this procedure, we are going to get a color in the following way. So from random map on simplex to coloring, we consider an edge, and so let us enumerate the vertices 1, 2, 3, and then we are going to color the nearest vertex of edge to the vertex to this vertex in color 1, the nearest vertex of edge to this vertex in color 2, and here in color R. And then we are going to evaluate the probability of contradiction, and after a lot of calculations, we have that we finally have a bound, some bound, and this bound admits, from the one hand, it admits a local form. From the other hand, if somebody if somebody starts from the replacement R on a bigger number A as at the beginning of the lower bound, then we will get the same bound as the simple one was. So, like with another constant, C this ratio and this so on. Okay. So I have 5 minutes, yes?
Yes, you have 5 minutes.
Okay. So let me note that also we can construct if R is not very big, we can construct an explicit example of a hypergraph which doesn't admit panchromatic coloring, using the ideas by Heidi Gebauer, who so we can make an explicit construction using her ideas. She gets an explicit example of a hypergraph which doesn't admit proper 2 coloring, a proper R coloring in the standard sense. So, and here we also have with right exponential. So, and here we also can do the same. So we can get a hypergraph with this number of edges, which doesn't admit coloring panchromatic, and it's very explicit and very simple construction. Okay, so now I would like to finish my talk about panchromatic colorings. And then I would like to ask you one question, doesn't connect with this. So I finish with panchromatic colorings.
But you want to ask a question?
Yeah, but maybe we can.
Now you want to stop here?
To stop here?
Yes, I see.
Questions, maybe some.
Okay, thank
comments.
you very much for your talk. I understand. Okay. It's an interesting situation, but now we have to make some discussion about this problem and then probably proceed to a question of Danila. So any questions or comments concerning this talk? No questions and comments. Now there is a question by Danila. Okay, let us.
Okay, so. So let me. There is definition of intersecting families. Intersecting family is a hypergraph such that every two edges have non-empty intersection, yes? And Erdős and Lowas asked a lot of questions about coloring such hypergraphs. So I would like to ask you the following question. If we so there is another definition of cross-intersecting family. It is a triple vertices, edges, such that every edge of the first type intersect intersect. Sorry, I just missed not inequality here. Not equality here. So intersect every edge of the second type. So do you know anything about coloring of such hypergraphs? It's my question.
As I understand, no answers right now. So probably it's better to postpone this discussion, I don't know. Yes, let us thank the speaker once again. And